Hi, I'm Ned, and I make games. Today, I'm making a toon shader with Unity's shader graph. Along the way, I'll set up custom lighting, something useful for a wide variety of shaders. The complete toon shader will support textures, shading ramp textures, shadows, specular highlights, and multiple light sources. Toon shaders, also known as cel-shaders, break shading into distinct segments, creating a cartoony look. They're a good way to add character to any game. To build this shader yourself, you'll need Unity 2019.3 or later, and some basic knowledge on how to use materials and the shader graph, a script editor like Visual Studio Community or Visual Studio Code, and an image editor like Photoshop or the GIMP. One more thing before we get started. I made this shader in Unity 2019 3.13 F1. If you encounter any problems with a later version, look in the comments. I might have a solution there. I highly recommend creating a fresh project to follow along with me. It will be simple to integrate your new shader into an existing project when you've got it working. Open the Unity Hub and create a new project using the 3D template. Download the Universal Render Pipeline package through the Package Manager. This enables the shader graph in your project. To have Unity use the Universal Render Pipeline, create a Universal Render Pipeline settings asset. Assign the pipeline asset in Project Settings. Create a Shaders folder and an Unlit graph asset. Name it Toon. A shader by itself is not enough to draw a mesh, it needs a material. Create a Materials folder and a material called Test Toon. Assign it to use our newly created toon shader. In order to test the shader while working, create a test scene. Import some models and set up the camera and lights. Give the objects the test toon material. They'll turn into gray silhouettes, but that's okay. The toon shader does nothing at the moment. It's time to program the shader. We need to calculate lighting from the main sunlight, the directional light in the scene. To calculate the amount of light a surface receives, you need its normal vector, which is the vector that points directly outwards from the surface. The closer to parallel the normal vector and direction of light are, the more light the surface receives. A function called the dot product can calculate this. It returns 1 if two vectors are parallel and 0 if they're perpendicular. The final value, which I call the diffuse lighting attenuation, is a multiplier for light color, giving the final color for the surface. Okay, so let's program that. Open the toon shader, which is almost empty right now. Unfortunately, it's not simple to get light information in a shader graph, so we have to write some shader code. That's where the custom function node comes in. Right-click on empty space and search for custom function to create one. Go back to the main Unity window and create an includes folder. Open that folder in your operating system and create a text file named Lighting.hlsl. Open that file in your preferred script editor and write this calculate main light function. You can look in the video description for text to copy and paste. This is the function name. The float suffix tells Unity which type of numbers to use. The function arguments appear next, both inputs and outputs. World pose, or position, is an input, while direction and color are outputs. You can tell this because of the out keyword. All arguments are float3 type, which is a 3D vector made out of float type numbers. Look at the function body. This is a preprocessor directive, which tells the compiler to use different code under different circumstances. In this case, if the shader is running inside the shader graph preview window, it will set predefined values for direction and color. If it's outside the preview window, we'll call this getMainLight function, which is defined by the Universal Render Pipeline. GetMainLight returns a light structure containing values for direction and color. You might notice more preprocessor directives at the top of the file. Put simply, these prevent Unity from including multiple copies of this function in the final shader. Return to the shader graph. Click the gear on the custom function node to edit its settings. Add one vector3 input called world pose and two vector3 outputs called direction and color. Set the type to file, the name to calculate main light, and the source to lighting.hlsl. These fields are case sensitive. The function node should display a yellowish circle in its preview. If there's an error, first check for typos. Create a position node and set the mode to absolute world position. Drag the out field to world pose. That finally gives us the light direction. With this normals node, we also have the model's normal vectors. Hook both values to a dot product node. For lighting, we want to discard any negative results, so we can use a saturate node. It clamps values between 0 and 1. The final result is the value for diffuse lighting attenuation. Multiply that with light color, and you have the final color. Click Save Asset in the top left corner to compile the shader and check out the scene. The meshes are 3D once again. Ramp textures are textures containing a grayscale gradient. They're a good tool to achieve a toon-shader segmented lighting style. Use the diffuse lighting attenuation value to read a pixel from the ramp and multiply that with the light color. This method gives complete control over the lighting gradient. When graphs get complicated, it's a good idea to separate different parts into subgraphs. Create a folder to hold these subgraphs. Open Toon, select these nodes, right-click, select Convert to Subgraph, and then Save as Calculate Lights in your new folder. Subgraphs can have outputs, and Calculate Lights should have two, a vector 1 called Diffuse, and a vector 3 called Color. Click the gear in the output node to set this up and save the asset. Return to the main Unity window and create a Textures folder if you haven't already. Create or import a ramp texture. Here's one I'll use. Make sure it's oriented horizontally. Open the toon graph again. To access the ramp texture, add a property. This is a variable passed to the shader from the material. Click the plus icon in the Properties panel to add a Texture 2D property and name it Toon Ramp. To sample or read from the ramp texture, we'll need a Sample Texture 2D LOD node. Create a ramp texture property node and feed it into the sample node. Use a sampler state node to tell the shader how to read the texture. Specifically, set the ramp mode to clamp. Graphics programmers call texture coordinates UVs, where U is the column and V is the row. When sampling the ramp, set the U chord to the diffuse attenuation. The V chord doesn't matter right now, so set it to 0. Use a vector 2 node to create this coordinate. The output from the texture sample is the final multiplier to the light color. Hook everything up and save the asset. Return to the main Unity window. Set your ramp texture in the toon material and see your test scene in all its toony goodness. So we have toony shading, but it's lacking color. Let's add support for diffuse textures. First off, create or import some textures to use in the project. Open the toon graph. Select all these nodes and create a subgraph called Calculate Lighting Ramp. Unity automatically defines some properties which act as input fields in subgraphs. Rename the properties to Attenuation, Color, and Toon Ramp by right-clicking them. Also, rename the output value to Out. Save the asset and return to Toon's graph. Reconnect any nodes which got disconnected. Add another Texture 2D property and name it Diffuse Texture. Create another Sample Texture 2D node and a UV node to get the model's UVs. Notice I left the sampler state unconnected. Unity will use the settings specified in the texture importer. Multiply the texture sample by the light color from Calculate Lighting Ramp. Save the asset, set your textures in the materials, and watch your models come to life. One feature conspicuously missing so far is shadows. Unfortunately, Unity makes it difficult to implement them in a shader graph when you're using custom lighting, but I'll walk you through it. Open the shader code file, Lighting.hlsl. We need to add some shadow logic to the calculate main light function. Add two additional float outputs, distance atten and shadow atten. These hold the attenuation of light due to distance and shadows. In the shader graph preview block, set these new variables to 1. Notice a hash if block with shadows screen. Put simply, there are two types of shadows Unity can compute, and you must call different built-in functions depending on the type. Regardless, pass the shadow chord value to get main light and set the values for distance atten and shadow atten from the light structure. Okay, so we're done with that file. Open the Calculate Lights graph and click the gear in the Custom Function node to add two new Vector 1 outputs. distance attend, and shadow attend. Combine the attenuation values by multiplying them together, and then multiply that with the diffuse attenuation. We're all done here, so save the asset. It might seem like that's all that's needed to support shadows. Unfortunately not. In the universal render pipeline code, there are several keywords, like the shadow screen we saw before, which control how shadows work. For good-looking shadows, it's important to enable 3 different keywords. Most are turned off by default, so no shadows will display even with our modified code. As of now, the process to turn on keywords is kind of complicated, but here's how to do it. Open the toon graph. In the Properties panel, add a new keyword of Boolean type, and then 2 more for 3 in total. On each, set the default to on, the scope to local, and the definition to multi-compile. In the reference fields, enter the 3 keywords we need to enable, 1 in each property. Capital letters and underscores do matter. Okay, so save the asset. Return to the main Unity window and select the toon material. In the upper right of the inspector, there is a 3-dot menu button. Click that and switch to debug mode. You should see a shader keywords field. In that field, fill in the 3 keywords we want to enable, making sure to leave a space between each. Again, capital letters and underscores matter. Press enter and then disable the inspector debug mode. That might be all you need to do to see shadows. If not, there are a couple things to look at. In the Universal Render Pipeline settings, edit shadow settings, specifically set lighting, main light, cast shadows to on, set shadows, cascades to at least 2, and shadows, soft shadows to on. Also, check that the camera has render shadows enabled. Keep in mind you will need to add these 3 shadow keywords to any material using the toon-shader. Hopefully, Unity will make this simpler in the future. The little glint of light you see in eyes or on glass marbles is called a specular highlight. Specular lighting adds a lot of character to a model, so let's add it. The algorithm to calculate specular lighting is similar to that for diffuse lighting, but a little more complex. Highlights come from light reflecting off a surface and hitting the camera. We can approximate this by taking the average of the light direction and the camera direction, and then calculating how close to parallel that vector is to the surface normal. Open the Calculate Lights graph. Create a view direction node and set the mode to world space. Calculate the average of 2 vectors by adding them and then normalizing the result. That will bring the vector's length back to 1. Finish the algorithm with the normals, dot product, and saturation nodes. If you looked at the highlight right now, it would be very large, so let's shrink it by adding a new vector1 property called smoothness. Plug smoothness into this formula and use it as an exponent on the dot product result. Since the dot product is always less than 1, taking it to a higher power will lower the value, shrinking the specular highlight. You could stop here and use this value as the specular attenuation. I found that it creates some weird highlights and shadowed areas as is. To eliminate these artifacts, multiply by the diffuse attenuation. Add a specular vector1 field to the output node and then save the asset. Let's add a specular lighting ramp. It needs to be different from the diffuse ramp, but it's more efficient to load as few textures as possible. Just draw the specular ramp above the diffuse ramp on our image file. Combining them into one file satisfies both problems. Now it's important to change the V chord when reading from the ramp texture. It needs to be set to 1 for the specular ramp and 0 for the diffuse ramp. In the Calculate Lighting Ramps graph, add a new vector1 property called ramp sample V. Route that value into the Y input of the vector2 node. It's time to wrap everything together. Open Toon Graph. Create another Calculate Lighting Ramps node and set Specular as the attenuation. Set the appropriate ramp sample V values and connect properties together. Don't forget to create a smoothness property in this graph as well. Finally, add the specular color and the diffuse color together. Save the asset and check out the scene. Fine-tune smoothness in materials until everything looks just right. Wouldn't things look even better with more lights? Let's implement them. We need to dig into shader code some more, but first a little background on how Unity handles lights. Unity stores the main light that we've been using separately from other lights. Such additional lights must be handled specially by the shader. Additional lights can be of two types, point lights and spotlights, also sometimes called cone lights. With that out of the way, let's tidy up the graph and get ready for more complexity. Open Calculate Lights. Select just about everything and create a new subgraph called Calculate Main Light. Edit it and verify that smoothness was carried over and the outputs are named correctly. We'll need the algorithm to adjust smoothness elsewhere, so select these nodes and create a subgraph called Adjust Smoothness. Edit it and rename the property to in and the output to out. Make sure everything is still hooked up and save all graphs. Return to the main Unity window. Create a new shader subgraph called Add Additional Lights and open it. Our goal with this graph is to combine together the attenuation and light colors from all lights. Diffuse and specular attenuation from each light can simply add together. Light color, on the other hand, must use the weighted average color between all lights, where the weight is that light's attenuation. Since we don't know how many additional lights there are, we need to loop through them. Loops are not possible purely in nodes, so we need to handle this in the hlsl file. In the Add Additional Lights graph, add these properties, which give smoothness and main light information. Next, add 3 outputs for the 2 types of attenuation and light color. Create a custom function node. Open the Lighting.hlsl file and add the following new function, Add Additional Lights. Note this function has 7 inputs and 3 outputs. There is a familiar preprocessor directive, this time meaning the code inside will not execute if in the graph preview window. getAdditionalLightsCount is a built-in function in the universal render pipeline. It returns the number of additional lights currently affecting the model. getAdditionalLight gets a light structure just like getMainLight did. These lines calculate the diffuse and specular attenuation. They're the same algorithms we built in graph earlier, but in code form. Add the results to the running totals and add the weighted light color to the total. Outside the loop, divide the total light color by the total attenuation to calculate the final light color. There's only one caveat. If the total attenuation is 0, set the light color to the main light color. Always avoid dividing by 0. Back in the Calculate Additional Lights graph, fill in the arguments, outputs, and setting information corresponding to the function we just wrote. Like before, double-check for typos. Now create nodes to hook up all the needed inputs, including an Adjust Smoothness node. Finally, connect the diffuse and specular outputs to the output node and save the asset. Next, edit Calculate Lights and add the new Add Additional Lights node. Route nodes together and save that asset. Okay, so that's it. Create some point and spotlights and watch things light up. Make sure the light intensity is high enough to be visible. If they're still not showing up, check the universal render pipeline settings and set Lighting Additional Lights to per pixel and the per pixel object limit to at least 1. And with that, we're done. The shader is in a good spot, but there's always more features you could add. Here are a few ideas if you're feeling inspired. Ambient lighting, rim lighting, texture tints, specular tints, specular maps, and normal maps. Try to implement a few. Thank you all for watching. If you like this video, please leave a like. It lets YouTube know they should recommend this video to others searching for toon-shader tutorials. If you have any questions, don't hesitate to leave a comment. I have 2 questions for you. How are you planning to use this toon-shader in your project? And are there any topics you'd like to see a video about? Thanks so much for watching, and make games!